All right, we can get started here. So this is the, I think not should be lesson 4, should be lesson 5 or 4-2 about DTI atlases, fibers, and profiles. What we had last time, we looked at the unbiased atlas building, how to run DTI Atlas Builder, and today hopefully we'll get through the rest of it. I'm trying to be a little faster than last time. This is again the overall diffusion analysis scheme that we have here. So we have some first quality control that's happening. In our case, we're building an atlas, and that's what we talked about last time. And then the atlas gets into an automatic tractography so that we get the best tracts as a reference of analysis on that atlas, and then extract profiles from those tracts and analyze those profiles in FADTTSter. And so the next step is I will look at this. Now, while by the way, particularly down here, these are all different tools. The output of one tool usually is the input of the next tool. So it's possible, particularly on the command line, to streamline all of these together in the script, although we currently are not doing that. The reason for that is that anyway, after each tool, usually you want to do some quality control. But theoretically, you could plug this all in one mega module if you would want to. So yeah, so first, how to do tractography. So we have an atlas from our data, and in that atlas, we would like to get tracts, and tracts should be defined from that atlas, directly on that atlas. For example, we're interested in the uncinate or the GNU. Where is the GNU in that atlas? And once we have that, we can do an analysis of the GNU across all our subjects. This used to be all done manually. Some of you may remember this. If we created a new atlas, this would then take weeks to generate all the fiber tracts that we were interested in, because usually we're not just interested in one fiber tract, but in 10 or plus tracts. Now we've automated this a little bit. The reason why this was so time consuming, and also why it's very highly variable across different raters, is the seed region specification takes a lot of time. And it can be like, if you do it slightly differently, that seed region specification, you get a very different tract out of it. Then once you get tracts, you have to clean up those tracts. That's very time consuming and variable. And then even though you may think you know what the uncinate is, if you ask somebody else, their view of what an uncinate is can be quite different. And you can see that if you look through literature, the definition of the tracts from different DTI atlases are similar, but they're certainly not the same. There's actually quite a bit of variability to them. So the idea would be to have this fully automated. Now, we're not yet there, and there's really no good method out there that does this fully automated. There are some methods or some tools that do a fully automated analysis based on this, but you have to then be willing that the tracks that you use for the analysis are slightly imperfect. So if you want to have, let's say, perfect, or let's say if you do a hippocampus segmentation, you want to be the hippocampus and not have also a little bit of amygdala in there. Same thing here. If you want an uncinate and not a little bit of ILF in there, well, then you need to have some manual interaction. So it's not fully automated, but we can do something in between, which is this thing here, which is semi-automated. And that's where AutoTract comes in. So AutoTract tries to do this fully automated, but I don't think the quality is there that you should accept, basically, the fully automated results, but actually do some manual correction from that. And so what you would do is you would first run AutoTract, and then you would run 3D Slicer as well as Fiber Viewer Lite to remove unwanted parts. These two tools slightly have different views, and really Fiber Viewer Lite, we only need one little thing in there, and I'm pretty sure we actually implemented already a slicer module that replaces this one here, but I cannot remember where the CP student stored that module. We'll probably have to re-employ it because we lost it. Anyway, we'll get to that. Yes, so AutoTract is trying to automate what you would do as a manual rater. So when you would go get your atlas, now you would want to do, let's say, track the ultimate. How would I do that most consistently as a manual rater? So what AutoTract does is basically it uses an existing atlas with known tract definitions, kind of like when you would look up in the book or anything like that, except for here the atlas is going to be an image with tract definitions. It will register that atlas to our new atlas that we created from our study. And we then use these propagated tracts to do a seed propagation for creating tractography on the new atlas. Now, that will yield lots of tracts, not just the tract you're interested in, but kind of like an optimistic view of that tract, much more than the actual tract you're interested in. And then we have a final step, and that's where we're using deep learning to basically label those fibers, whether they belong to the tract of interest or to another tract. That's the GUI that you have in AutoTract. You can, as with the other tools, you can run that on the command line, but particularly at the beginning, you probably want to run this with the GUI. The input, if you don't want to specify a lot of details, you want to use the default values, is rather straightforward. You basically need your input DTI atlas, so the atlas you created from your data. You can also use this to track an individual data set. So rather than the input DTI atlas, this would be then just your DTI image of your individual. And then you need basically set the output directory and the reference DTI atlas. So where is that atlas where we have our tracts already defined? All the optional stuff here is rarely used. You're much more likely to edit some parameters. If you feel that you want to specifically tell the tool where is only white matter, you can do that, or where is the CSF. The reasons why these are used is when we do the tractography, we restrict the tractography within the white matter, and it's not allowed to go outside the white matter and into the CSF. That's why we have these two masks. In general, these masks are automatically determined by the program, and they're determined generously. So, and that's perfectly fine in the usual way.
So what's the displacement field?
The displacement field is if you don't want it to do the registration. So if you want to say, oh, I've already done the registration, let me give it to you, that's that displacement field. If you provide that displacement field, it will skip the registration step. And that's this next slide that I'm talking about. So this is the main way to propagate the information that we have in the prior atlas to your current atlas or image that you want to have tracked. In this particular case, that prior atlas or template has to have a DTI image. You don't need an FA or anything like that, just a DTI image. It has to be in NERD format at the moment. And it has to have with it fiber tracts. And these fiber tracts have to be defined as VTK files, as is the standard in Slicer. And you can have any number of tracts. So what you would do is you say in the first tab, you have your reference DTI atlas that you can select. It's just a file, the actual DTI file. Then in the second tab, you select your tracts directory. It will directly look in that tract directory what kind of VTK files it finds and lists them here. And then you can select all the tracts that you want to have tracked as well. You can just use all of them or only individual ones. The reason also why you're allowed to uncheck and check these is because this procedure is rather time consuming and also uses a lot of memory or space on disk. So it's quite common that you don't want to track stuff that you may be not interested in. Then once you've defined this, the tool will do a registration of that prior atlas to your current image, and that uses the same registration as DTI Atlas Builder does. It's a tool that's called DTIReg. That's one of our slicer modules that registers two DTI images to each other. So the best thing, if you use that, you can use exactly the same settings for how to run DTIReg that you've already used in DTI Atlas Builder. These are just standard ANTs-based settings, basically. If you're used to ANTs, this is relatively easy to set, and I'm not talk too much in detail, but the main thing is that it's probably good to use here the same settings to what you used when you created your atlas. AutoTract will actually create in the output folder then a new folder for the registration. I think it's called one.registration. And in that folder, it will have registered DTI as well as the propagated tracts and etc. They're now on disk and saved. And now that we have those tracts in our own data set, no longer in the template space, but in our own data set space, we do not assume those tracts are perfect. We want to have new tractography done on our data set, and that's done by first voxelizing those tracts, meaning making out of those tracts a label map, and then we dilate that label map so that we have an optimistic tractography, meaning at least the tracts we're interested in, but probably a little bit more. But we want our tract to be in there. And that you see here in the tractography, you can change the dilation radius. Dilation radius by default is set to 2, and that's measured in voxels, because dilation is in voxels. And then what it does, it does with that seed region, it does the standard slicer region-based tractography. We've been thinking about to add additional options in here, but that to use other types of tractography, we just haven't done that yet. And these settings is what you would set also on the slicer interface. So if you're used to how to do tractography in slicer, those are exactly the same settings that you would use there as well. Again, the main thing is that here the output is an optimistic tractography. So you're getting at least the tract you're interested in, but probably much more stuff that you don't want and have to get rid of. The default parameters that you get if you're working on human settings, probably you do not need to change anything here. Maybe if you have special high-dimensional data, high-resolution data, you can think about playing around here with the seed spacing. And if you have special infant data, you may want to play around here with the linear start measure and the stopping values, because the infant data has lower SNR and lower FA values, so you want to usually use those. The best way to get your best tractography parameters is if you play around with your atlas in slicer, just a few tracks to kind of like see what are the tractographies you get with that setting. And if you're happy with a certain setting, that's the setting you can then use in that tab. And then once you get this optimistic tractography, the next and last step is to do a classification. Basically, it classifies each fiber whether it belongs to a certain tract or not, or it labels a fiber with a tract name. Think of it like that. Now, of course, in order to do that, we have to have already a prior training algorithm and everything like that. So currently, we have trained two fiber classifications. One is for an infant, or for a pediatric diffusion atlas, where we have about 50 plus tracts, as well as one is for the primate atlas. That's Rosa helped with that one. Now, since this is a deep learning based approach, definitely something you want to probably run on one of the newer machines that have GPU nodes, or something that you want to run on Longleaf on one of the GPU nodes. What you have to, so here you have something called the model archive. So that's something that has to be given to you. As I said, we have 2 model archives for these 2 populations. And then it runs that classification. Now, as an example, what it does under the hood, it actually takes the tracts, and every location along the tracts determines curvature and distances through atlas landmarks. And that's what it uses for the classification. I'll show you this. For example, this is the arcuate fasciculus. And now if we would want to have data, we want to track these three parts of the arcuate fasciculus, the frontoparietal, the temporoparietal, and the frontotemporal part. We've had this defined on a lot of data sets for training, because that's one of the more complex tracts, the harder tracts to track. And the tool, but during the training phase, takes all the tracts that we want to train with and determines landmarks along the tracts, and then defines distances to these landmarks. And here you see actually distance to landmark 3, because this is the closest. You see red, and the blue is further away. And so it determines these landmarks automatically during the training phase. Now that would be if we were to train an arcuate-only classifier. And what we've done is actually a classifier that classifies, or in this case, 53 tracts. That results obviously then into 53 times 5, which would be 265 landmarks. Since that would be too much, what we're doing is actually we did a clustering to reduce that to only 32 landmarks, and removing landmarks that basically have the same meaning in the image. And those are the 32 landmarks that we end up with at the end. So we're taking the distances to those 32 landmarks and the curvature, and that's going to be used for the classification. And this is a visualization of that training. So those are the 32 landmarks that were used. We're highlighting it now landmark F1, and you can see the column map shows the distance to that F1, and it shows now the 3 parts of the arcuate, as an example, how each of them have slightly different distances and different distance patterns, so to say. And that's the pattern that the deep learning learns, basically the distance pattern for each of those 32 landmarks. And it combines these together, and then basically for every tract learns those patterns. So if you have tracts that have similar patterns, that's when confusion can happen, which is why it's not perfect. The nice thing about this one here, it's inherent to the brain. So it doesn't matter how your brain is actually oriented, as long as you have a registration of the prior atlas, which we have to do anyway. To this, we have everything locally defined, independent of the orientation. So that's what's going on under the hood. It has this labeling, and Mark can tell you there's a lot of problems with running that labeling, and sometimes you need to twist it a little bit. But assuming it ran and it all worked, you get now the cleaned up fibers, and then you can load that into Slicer and use the fabric bundle display option to clean that further up. There's also a way to use Fabric Viewer Lite to remove fibers that are too short and too long. This, rather than a demo, there's another view. Oh. I'm not sure what happened here. And I'm going to run this. Now, this is not how it would look like after the fabric cleaning. This is how it would look like before you would run traffic. Now, the fiber classification. This is just, but it shows that even if traffic would do a terrible result, it's actually rather straightforward to use the fiber cleaning in Slicer to clean up the fibers. Remember, you have to do that only once. And obviously, this was done by somebody who knew how to do this, maybe taking you a bit longer to do this. But what you do is basically you're defining the tracks that you want to keep, and then you find the parts that you don't want to keep and throw those out, and you keep updating the track until you're happy. And then you end up with this. So this was very quick. Obviously, it would be taking you a bit longer than that. The thing is, though, the actual tract that comes out of traffic looks much better than that. Now, FiberViewer Lite is really, it's only there to remove fiber parts that are too long and that are too short. It can do other stuff, it can do much more, but we're not using those parts actually in our analysis these days. What you would do, you would load your tract into FiberViewer Lite. You would use the length clustering, which is the first button, and it will give you a histogram of all the lengths that your tract has. And then you can change here and upper and the lower threshold to basically get rid of parts that you don't like. It also has a visualization here of the length where the shorter ones are blue and the red ones are longer. And so you can adapt these interactively until you're happy with the tracks you get. One thing that you are prone to get if your tractography parameters are more optimistic is actually tracts that kind of like fold on top of each other. You'll see tracts that go all the way to the end and basically fold and come back. You really make sure to get rid of those. That you can easily do by just, reducing the upper threshold.
So particularly for an atlas, you probably just want that to be relatively uniform distributional lengths when you're...
Well, it depends on the tract. Yeah, and in the genome, I agree. But if we would look at, let's say, corticofugal tracts, you're going to have more longer tracts and more shorter tracts. We've been thinking about adding this automatically as a post-processing step where you would have also pre-trained distributions of lengths in there. And if you're outside those distributions, you would automatically get cropped.
Okay.
Like a very simple way to...
Fair enough.
That's something that we could probably add.
Awesome.
As I said, we actually have a module that does this in Slice. It even shows this nice things, but I cannot find it.
I'm sure somewhere.
Somewhere it is.
We'll find it.
Otherwise, I mean, actually to create this, it probably would. It's a great starting project for the incoming French students. It takes about maybe half a month to make this in Slice as a programming. So we can redo it as well. So that's how you get to your tracts. So we have now known tracts in our atlas in this semi-automated tractography. And from those tracts, we now want to extract fiber profiles and then analyze those fiber profiles. So those profiles are quantifying how much FA and DRD is along the tract. Now, there's two ways to do that. One way would be to look at the FA of your data as it has been mapped into the atlas space. That's actually what's commonly used if you would run the TBSS with FSL. Usually look at the data as it is in atlas space. What we're doing here is, because taking a tensor data set and mapping into atlas space, we have to have a whole number of assumptions when we reinterpolate the data in atlas space. We'd rather not want to do those assumptions. So what we're actually doing is we're going inversely from the atlas space back to the original data. We have the deformation field. We just use the inverse of that deformation field and look up the tensor in the original data set. And then from the tensor compute the FA, the MD, or the AD without need for any kind of weird interpolation assumptions that we may have to do. In order to compute a profile though, so that's how we look up the tensor values. Now to create a profile along the tract, we need to be able to make first a correspondence across the tract so that if we have one fiber and the next fiber, we can say point number 1 is the same as point number X on the other fiber. So we have to have some way to have a correspondence across the different fibers within one bundle. And that's done using an arc length parameterization, meaning we start at a given location, given cut plane, and at that any tract cutting that plane, that's location 0 for that fiber. And then we just walk along the tract and say any distance away from that center, that's the correspondence along the tracts that we're going to get. The one thing that you have to know here is, while we could extract exactly the value along each of the tracts, so if I, for example, am here, I could go and look up now in the individual data set what is the FA there. We're actually doing a convolution. We're doing a local Gaussian kernel that basically returns a smoothed representation rather than the exact representation. This just provides a much better, more smooth result. And the size of the kernel, that is something that you can adjust, but the default is pretty decent. Our methods determine this plane of origin automatically, so you rarely will have to change that. There are cases where the automatic procedures will fail, and I can draw that here. I'm sorry, that's not going to be on the video. But so if you would have, let's say, a fiber tract that looks like this, we would have a plane that goes like that. Now, sometimes what can happen is, because of the way the automatic method works, it's not going to be placed at the right place, and you may have a plane that more looks like this, let's say here. So that means a given tract could be cut at 2 places, not just at 1 place. And as soon as you have your plane not just cutting the tract at 1 place, but at 2 places, then it becomes ambiguous where that starting point is. And in such a case, you're just having a bad origination plane. Usually there is a way to determine visually an origination plane that only cuts the tract once, not multiple times. You can use Fiber Viewer Lite actually to visualize that plane and see how that looks. So in such a case, you would need to adjust those planes. We rarely see that. I think in the human brain, the only time we see that regularly is on the fornix, if the fornix travels too much anteriorly into the temporal lobe. Then our automatic methods kind of like gets thrown off.
What's the definition for the automatic method? What is it looking for?
Well, what it does, it goes along all the tracts, and it tries to find the center point, and then computes the median over all the center points that you have. And then at that median, it computes the plane that's orthogonal to the local fiber direction.
Okay, that makes sense.
And all of that is in DTIAtlasFiberAnalyzer. So that's the next tool. So all of that is in DTIAtlasFiberAnalyzer. You can start it up through Slicer or on the command line as usual. And if you do the GUI, you can also tell it no GUI, and that this doesn't come up. If you tell it GUI, then this is the thing that comes up. This interface allows you to put together all the information you may need all by itself, so you don't need an external editor to put together for your CSV file. It's based on the CSV file that provides you the information. Now, if you've used DTIAtlas Builder, you do not need to do too much. You just need to load here the output of DTIAtlas Builder. DTIAtlas Builder will give you a CSV file. So, assuming you've defined your data, whether that's now manually defined or you loaded the prior CSV file, the one thing that you need to set are these 3 options here. Basically, you need to tell the tool where in the CSV data is the information with the names of the subjects, where is the data with the path to the DTI data, and where is the information of the warping, the deformation field. If you get data out from DTIAtlas Builder, that's actually relatively straightforward. This is always the first this is always the second, this is always the last. So there may be stuff here in the middle, but all the other ones are pretty uniform how they are located. So once that is set, you're going to click on next. It's here. So you have to set your output folder. Not forget, obviously. Where is the output going to go? And in the next step, you're going to defining what are your tracks you're going to be using. Now these are the tracks that you generated with AutoTract. So you have your tracks generated with AutoTract. You plot the folder here. Here it will list the fibers it detected in that folder, and you basically push those fibers over to this side, and those are the fibers that we're going to be analyzing. So rather than having checkboxes like in AutoTract, here you kind of like have two things, like the fiber possible for analysis and the fibers that are analyzed. Once you specify that, it's all done, you click on next. And what it now does is the step where it goes and looks up all the values in the original space. And so you get, for each of your tract, you get a new tract, but now sampled for that subject. In the next step, we're going to be, from that, after that sampling, we're going to be extracting the profiles. And here, it will list all the tracts that you selected first. And then for each of the tracts, it has either, it gives you an option to select its plane file. So if you want to manually define that plane, that's where you would select the plane file that you manually did. As I said, that's very rare. You should be needing this. Usually you're just going to see your fibers here, and you make sure that this one here says median point of fibers. That's the default, so it should be there. And then you click apply and go. And you say which properties you want to analyze. So usually, I think the default has them all selected. You definitely want to not do all, it's too many. But usually you look at FA, MD, or DAD. So usually you select those, and then say go.
Actually, the default is just FA.
Okay, thank you. So the default is just FA. So if you want to do more than FA, you select those. One of the parameters here is the tract samplings. That means how many tracts do I sample along the tract to create a profile. Right now, this is so it's in millimeters. Right now, this is at 1 millimeter step. You can definitely change that. Just that means you get a more finer profile. Particularly if you high resolution data, one could think about for that to go to something less than a millimeter. Certainly if you have primate data, you want to go less than it. Otherwise you don't have many steps.
I'm sorry, can you truncate it? Oh wait, I don't think I saw an option for it.
What do you mean truncating?
Like, so if you wanted to go finer from the origin and then go smaller steps and stop it.
So it will always go to the full end. It will always go to the full end.
Just the
And because certain tracks don't have uniform length, some tracks are longer, some tracks are shorter. In the output file, not just will it list you the profiles, which is the average, in this case, let's say FA, at that given location, but it will also tell you how many fibers were actually having that value. So how many fibers were used to compute that average. And what you'll see is to the ends, you'll have less and less fibers. And if you want, you can always then crop or, at the end by saying, okay, I don't want to use the data that's based only on a very few set of fibers. That's always possible. So this is the output organization from the DTIAtlasFiberAnalyzer. As is the case for most of our tools, it saves all the parameters that you used for the analysis. And then it has a case folder where it has the track as it has been sampled in the original data set. That's this just gene.vtk. The process.vtk is now the tract sampled with the plane. So this is, in some sense, the same tract, but it has different points along the fibers. This were the original from the Tractography, And here it has been resampled with this origin plane being at 0 and so on. So, for example, here in the process, with the previous settings, the points among the fibers would be spread 1 millimeter apart, whereas usually your tractography is finer than that. Then the FVP is called Fiber Viewer Profile. That's why it's called FVP. That's a text file that contains the profile. So if you're interested, you can then directly use that profile for each subject, so to say. Now, the tool will also actually gather that stuff together into a nicer format so that you don't have to gather this. So it creates a fiber folder, where in the fiber folder, it has each fiber file. That's just the average fiber file. Actually, you need the fiber profile folder. In the fiber profile folder, per fiber you analyzed, it has a CSV for each of the properties you determine. So if you say FAMDRDAD, it will have 4 files with a CSV with the profile for every subject that you ran this over. And really, you only need this. Has basically all the values in there that you need for analysis. Right. So all of these statistics of the profiles, they're gathered into that single CSV file. And that single CSV file with the profile, you can give that now to your biostatistician, or you can analyze that yourself. And that's where the last tool comes in, and that's FADTTSter. You can also easily load this into Excel and plot your profiles by yourself. If you're interested, you can nicely chart those. You can also easily compute an average FA per tract, which is average the whole profile, if that's what you want to do. And we also have additional tools that actually takes this profile and subdivides the profile into parts of consistent high FA regions. So if you want to, for example, rather than an average FA across the whole tract, only want it over those regions that actually have good signal, then you can use that tool as well. But that's easy to do if you don't want to use the tool as well. You can also do it manually. Additionally, let's assume you've taken these profiles, given them to your biostatistician, or you analyze them yourself. Now you have p-values or other information along the tract. You can merge that back into the tract. That's a tool called Merge Stat with Fiber. What you will need is from before is you need that parametrized VTK file, plus your file that has the stats in there that you want to have visualized, and you give that to Merge Stat with Fiber, and then it will add those stats into the fiber. So that's basically what DTIAtlasFiberAnalyzer will do for you. If you want to look at those outputs, you can actually use Slicer as well as Shape Population Viewer. Slicer probably is right now the best way to look at it. So if you would load, in this case, the parameterized BTK into Slicer, you load it as a model. You don't load it as a fiber bundle anymore, because now it's processed. It may not have the tensor in there anymore. And so you load it as a model, and then on the model module, you can select the scalars visualization, and then you can change, so on the scalars, you can change which active scalar to view. If this is just after the parameterization, you're going to have 2 parameters here. One is fiber location index, meaning the index along the fiber of your profile, plus it also has a distance to the origin in there. Now there, of course, the 2 parts are directly correlated, but they have different values. And if you load at this, you can see basically here with a column map how that parameterization worked. If the parameterization failed because of that situation where you have a plane cutting twice, you would see that here. It would not look like nicely from one end to the next end, but you would see maybe 2 blue areas or 2 red areas that shouldn't be there. And of course, our tools will crash. You'll realize it that way too. Then what shape population viewer can be used for example, you could look at the FA of your subjects now. So you have, remember, each subject has been sampled in their own data set. It's in that cases folder. You could load now all these tracts and show the FA in each individual. You could see how actually the FA is different for each individual. We usually do not do that, but if you are the curious kind, you can definitely do so. It's definitely not needed for the purpose of quality control. Now, if you realize that you have a bad profile at one place, that's maybe where you want to go and look at that case's FA and see whether it looks like as expected. This is an example visualization for if you run now statistics and you propagate those back to the tract. And in this case here, it didn't even do the whole profile, but we got out of the profile, made it an average FA for the whole profile, and then we propagated back that whole profile, which is why you see each tract kind of like getting one single color. But it's, you can, even for this, you can use this merge stat with merge fiber merge stats. Now, so I've shown you how to define the fibers with AutoTract, how to use DTIAtlasFiberAnalyzer to get to the profile. And now there's also one more tool that allows you to do cross-sectional statistics. So this is called FADTTS. FADTTS is Functional Analysis Diffusion Tensor Tract Statistics, developed by Hong-Tu Zhu, probably about 10 years ago. And what's nice about this is it allows to have 2 types of analyses. One is it does a global analysis, where it doesn't tell you where along the tract something is up, but it looks at the tract as a functional unit. And so it will give you basic information whether there's a difference using the profiles between group A or group B. This is a 2-group testing way. Or whether there's a significant association, let's say, with gender or age with your profile. And it does that without, on a global level, without you needing to correct for multiple comparison or anything like that, even though we're looking at the whole profile. So that's the nice part of this functional analysis. Of course, usually we are then interested to know where things are different, not just, okay, the onset is different. We want to know, where is it different? Is it where along the tract? And is it just TFA, or is it FAMD, or all of them? So there's basically post hoc analyses from this, where we're doing a local analysis that combines first all FAMD, RDAD together, but at least now we know where. And then it has another post hoc, where what we also call post hoc in this tool, where we actually do separate FAMD, RDAD analyses. Now, because these are local tests, they have to be compared, corrected for multiple comparison. And that's also where your choice of sampling comes in. Because now we're comparing for how many tests we do. The finer we sample the tract, the more locations we're going to be analyzing, the more correction we have to do. So this, for this part here, it's good not to too finely sample your tracts. And we had then a French student, Jean-Noël. He created a GUI around this, around FADTTS. FADTTS is a MATLAB-based thing, and you can definitely create your own MATLAB scripts that call FADTTS, but it is actually quite complicated, and you can easily go wrong, which is why we wrote this FADTTster tool. FADTTster is actually quite nice. So first, you load simply your CSV files. That's the output of DTIAtlasFiberAnalyzer, so your FAMD or DAD. You can look at them and even edit some parts if you're not sure about this, as well as you have to load your subject matrix, meaning information about your subjects, which like age, gender, whatever you want to have tested. All of that has to be in that CSV file. Now, these files here only have your outcome variables, so that's your diffusion variables. This here will only have the subject data. So one is if you have your general GLM where y equals some matrix AX plus the error. So this would be your FA values and all the other DTI, and this is your subject matrix. And it automatically detects from your CSV of the subject matrix, assumes it has a header row, and it detects from the header row automatically what those different columns mean, and you can select which ones you want to use in your analysis right here. And here it gives you also a quick summary of what it detected in those files, meaning how many subjects it detected, how many points along the tract that your profile has, and same thing for here. It tells you how many subjects it has in the subject matrix file and so on. Now, rather than trying to make a subject matrix file that perfectly matches what you have on the other side for the MD-AD-RT data, we have a matching process. We just assume that the names at least have to match, and at least partially match. That's in the next tab. That's this subject tab, where it basically tries to match the subject matrix with the information from the diffusion. And on the green side is where it found the match, where it was able to match. And on the red side was where it found one information, but not the other. And it's missing part. Then you can go back and potentially correct information. Or if you find with all the stuff that's not matched, because you may have created more profiles than you want to analyze, then you're perfectly happy with having some red stuff here. And then for the analysis, if you don't want to use all subjects for which you have data, you can just simply deselect or select them here directly in the screen. In addition, you have down here another button that is for applying quality control to the profiles themselves. So if you click at that apply QC threshold crop profiles, what you will get is a view that looks like this. It opens up in a separate window. And it will plot all the profiles that you have. It will plot the FA profiles, also plot an average profile, and it has down here a threshold. That threshold is based on the pairwise correlation between the average profile with the individual profile. And so the assumption is that we're looking at a study where a low correlation with the average profile means this is probably bad data. It probably is a bad registration that happened, or something is bad about that data to begin with. Now, if you have a study where you're looking, let's say, at tumors or something like that in the brain, obviously this is not a very good assumption, because you may have actually tracts that go through the tumor in one individual and or a different place in another individual. So there, this one would break down. So this is our standard studies, let's say, in autism or typically developing kids or in Alzheimer or what have you, where you would expect overall the shape of the tract profile should be similar. In adult data, it's usually this threshold is around 0.9. It's because you'll see that because of the high signal to noise setting, this is usually pretty decently consistent. Now, in infant data, that's not the case. In infant data, because of the low SNR, you get into areas down here where the SNR noise are similar, so that there you have so much noise that the correlation quickly breaks down. And often, depends on the tract, that in infant studies can go all the way down to 0.7 or so. So that also means, for example, in our IBIS study, that very quickly goes down. Now, in our IB study, it also goes very quickly down because we have a crappy diffusion sequence with low SNR. Something else that Maria was asking about, like whether we could crop the tracts if they are more variable at the ends or maybe too long, etc. You can directly do that here. You actually, if you click on, where is it, the cropping, these two sliders here, you can put these sliders towards in and it will start cropping the tracts from the ends. And particularly if you see, for example, like this one here, you see the left end gets more variable as we go to the end. If you don't want that in your analysis, just crop a few sample points off. When you click that away and when you then start the analysis, it will write new files out with those crop profiles, with the subjects that were not good removed and everything like that. It will not overwrite your original files, but it will create for each of the analyses a separate folder, and in that folder it will write your selected subjects, your cropping, etc. That's all going to be in there. And in order to create that, we have to actually tell it to execute. And so the execution here, you need to specify where is your FATs, so your MATLAB FATs, where is MATLAB, because it needs to run MATLAB, and what's the output folder. Also, you have to give, this is done per fiber. So if you can, this is not done for all fiber jointly, but if, let's say, the ANSINET, you run this for the ANSINET, so you have to tell it that you're running the ANSINET so that the output files are appropriately named. Now, if you don't care how they're named, then you can just leave it fiber name. And there's really one thing that you can adjust here, which is the number of permutations. This analysis methodology uses permutations to test whether there's significance. And the lower number of permutations that you choose, the quicker it is, but also the less accurate. By default, it has 100. That 100 is too little. It says here, use 100 when testing, just to see whether things are working. Use first one with 100. It's working well. Okay, so now you're good. Now you put it to 1,000. 1,000 is kind of like a minimum. Anything above that usually is not necessary. You can go all the way to 10,000 if you're worried that you're not appropriately sampling. And it also depends a little bit on the number of subjects you have. So the higher number of subjects, actually the higher the number of permutations you should use. But if let's say, if you go this to 10,000, I cannot see any setting where that's not a little bit overkill. So if you go to 10,000, you'll always be fine, but you also wait much longer. And when you click on Run, it shows the output of the MATLAB here in this window, and it will start rolling. Now, this is quite time-consuming, so you can do this on Longleaf or on one of our servers. So then, once it's finished, FADTTSter has also an additional tab where it can plot all the output. And it's really nice, that plotting. It has a lot of configuration. It can be very much adjusted to what you want to show. It can create nice visualizations for your paper, etc. One of the things that, for example, it can do, it can display the raw data. It can display the raw data according to a prior binary value. So, for example, that it could show, in this case, it uses gender, like 2 plots for mean and standard deviation of the raw data in gender. But any binary variable that you give it, it can plot here. And you can do that for FAMDRD, which you select here. Then, so that's the raw data. That's prior to do the analysis. Once you have analysis data, you can show your betas from the GLM, so that what of your variants went into that covariate. So you could either show it by covariate. This is, for example, showing the beta of the gender, or by diffusion properties. And then it shows all the covariates. I'm not quite sure you can read this. I think blue line is gender, then it's gestational age at birth, days in birth, and so on. This is from a typical development study. And you can select here which ones you want to show, and it will have automatic this one here. You can change the colors if you would want to do. The main thing here, if you look at the betas, is that betas have a sign. So you can actually interpret whether the covariate affects your value positively or negatively. In this case, for example, we look at AD. Anything above 0 would be associated with a positive correlation. Think of it like that. So, for example, this is what is up there. Green group. I don't know what that group is. Whatever the group is here is positively. AD is positively associated with that group, whereas something like here, which is stays since birth, is negatively associated. So, meaning that the longer it's been since stays since birth, the lower the AD values. That's the negative association. Also, it allows you to show a combined display of the p-values. You can show the p-values only. I do not have a figure for that. But it can combine the p-values with your betas, where it shows with dots, basically the regions that are significantly different. And this is following, so you see here, for example, different covariates have different significance. So this particular thing, days since birth and gestational age at birth, are very highly significant, whereas other parts have lower significance. Some places where it is significant, some places not. Now, you can see here, this is omnibus. So here, FA, MD, AD, RD are tested together. So you don't know whether the significance is due to only FA or MD, but just looking at them jointly, there's a difference there. And this is FDR, meaning it's corrected for multiple comparison using false discovery rate at an alpha of 0.05. By the way, this here up here, it doesn't write that. We added that to the slide. That's just what basically is this one here, and you hopefully can select here whatever you want to see. And that is my last slide for today. Any questions about stuff we talked about today?
Just one quick one.
Mm-hmm.
So the DTI fiber analyzer, in past iterations, you needed to run one fiber at a time. There's some crossed off.
So no, so if you want to speed things up, and you want to run multiple fibers in parallel, then you have to run each of the fibers with its own output directory. So you cannot have, like if you run, let's say, 4 versions of DTIAtlasFiberAnalyzer, one doing the Antonet, another one doing the Chinu, they shouldn't write into the same output folder. If they do so, they can be mixed up. But yeah, you can run as many in parallel as you want, as long as the output folder is different. And the reason why, anyway, you may want to do that is because it takes a long time. And if you, let's say, have MD, AD, RD, which one is missing? MD, whatever, that's 4. And you would have, I don't know, 100 subjects. That's 4 times 100. And let's say you have 50 tracts, that's 4 times 100 times 50. That means even if our fiber sampling is fast, adding it all up takes a long time, just because we have to do it so many times.
So when you say each fiber needs to be in its own separate directory, you mean that there needs to be a directory of the actual
It means the output folder specified in the first tab, where you're saying where all the output goes for DTIAtlasFiberAnalyzer. That has to be a separate folder.
Okay.
And that's, in some sense, that's a bug actually about DTIAtlasFiberAnalyzer, because to tracks should actually not touch each other, even if they have the same output folder. There's no overlap in output files and so on. So we're not quite sure why it messes things up, but we know it does. So let's write it into separate folders. Good.
Thanks, Martin.
Thank you.